Okay, hello everybody. So I'm going to go through the concepts from problems 1 through 3. Okay, so first question is, what is a map and what is a function? So first of all, map and function are the same word, so they're the same thing. Okay, so they're the same, but what are they? First example. So this is how we write down a map. It says that xy goes to x squared y plus 3. So what this means is like the point 2, 1 in the plane goes to 4 times 1 plus 3, which is 7. So it's an assignment. Here's the assignment arrow, where 2, 1 maps to the point 7. So a point in the plane goes to a real number. The point 3, negative 4 would go to 9 times negative 4 plus 3. What's that? Negative 36 plus 3 is negative 33. So this is the point 3, negative 4 in the plane. So I might visualize it as like 1, 2, 3, 1, 2, 3, 4, like there. And that point gets assigned to the number negative 33. So I've envisioned negative 33 sort of hovering over that point, because negative 33 is the number here that was assigned to the point in the plane. Okay, so that's one example. Let's do another example. Here we take points in the plane and assign them to points in the plane. So like the point 1, 0 goes to the point minus 0, and then x is 1, 0, 1, okay. The point 1, 1 goes to the point, okay, well, minus y is minus 1, and then x is 1, so 1. And 0, comma 1 would go to minus 1, 0. And so we can actually visualize this as like, well, here's the point 1, 0, here's the point 1, 1, here's the point 0, 1. And each of those gets mapped over to the plane. 1, 0, this point goes to 0, 1. 1, 1 goes to minus 1, 1. 0, 1 goes to minus 1, 0. Okay, and later we'll see a different way to visualize this. Okay, so now those are two examples. So what is a map? What is a function? It is an assignment of every element of the input space to some element of the output space. So that is what it does. It's an assignment. Really, it's an assignment. So here the input space was R2 and the output was R. So every element of R2, every point in the plane, gets assigned a real number. Okay, so second question. What is the notation F colon Rn and then arrow Rm? Also, x maps to f of x, y equals f of x. Okay, so first we'll do some examples. So here's an example. Let's maybe give ourselves a little more room. Okay, so this is sort of the x maps to f of x notation. And here we're sort of seeing how to unpack this. Really, x, this is an element of R2, and over here we have 1, 2, 3 pieces, 3 components, 3 coordinates. So this is an element of R3. So x is secretly x1 comma x2, and f of x is secretly f1 of x, f2 of x, f3 of x. And so you see that we have 1, 2, 3 functions. Here's the first function, the second, and the third in this example. And if we wanted, we could even unpack the x and really say this is f1 of x1, x2, f2 of x1, x2, and f3 of x1, x2. So the idea here is that in this notation, if we're mapping from R2, so if n is 2, to R3, then x really has 2 components. F of x really has 3 components. And I'll write down that word component, coordinate. These are the same word. They really just sort of mean piece or a number, one of the numbers. Now what is this y equals f of x? So let's go back to our example. So here, let's pick a different color, blue. So if I gave coordinates y1, y2, y3 to R3, and I maybe want to name the coordinates of R2 as x1, x2, then I could write this map here by saying that y1 is equal to 5 sine x2 cos x1. y2 is equal to 5 sine x2 sine x1. And y3 is equal to 5 cos of x2. So this is sort of the y equals f of x notation. And what it means is that we're naming the output space. We're giving it names. In this case, R3, the y is secretly y1, y2, y3. And the f is secretly having, well, it needs 3 components. So it's secretly all 3 of these. Okay, so maybe that explains the y equals f of x. Now, what is the notation? Blah, 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 blah. So maybe I'll say that this piece, Rn, is the input space for a map. And the map has name f. Rm is the output space for f. Okay, so that explains that notation. Here, what is this notation? X is an arbitrary element of the input space. We named the input space. And f of x is the output assigned to x. Remember, a map is an assignment. And so f of x is our name. We named the assigned value. Okay? And y equals f of x. Let's maybe take this over here. My answer to that would be that y is the name, another name really, because we already sort of called it f of x. Y is another name for the output space. Okay, excellent. Okay, let's move on to the next question. What is the image of a map? What is the image of a map? Okay, use the previous example. So let's look at the previous example. Here it is. This map goes from R2 to R3. The image is the set of all the points in here. And so actually, we will learn this in problem 1. The image of this map will be a sphere. The image is a sphere of radius 5. So inside of 3-dimensional space, I can go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And I could try to draw, I'll do my best to draw this. 5, 4, 3, 2, 1. I don't know. This is tough to draw a sphere. That's my best job. So the sphere is sort of this two-dimensional object, a surface, not the interior, just the shell. Okay, so this is a map. The map sends a point in the plane to a point in 3D. And the image are the set of all outputs. All the possible outputs, in this case, turn out to form an object that has a name called the sphere. It's like the surface of a soccer ball is a sphere. And that's the image. So it's a set of all outputs. So, let's write that down. So I did the example. Now what's the image of a map? The set of all outputs living inside the output space. So, R3 was the output space, but we don't, this map here, I'm telling you, this map does not hit every point in R3. It only hits the points that are radius 5 from the origin. For example, this point way out here is never hit by our map. So it's not in the image of the map. Next, what is the preimage of a point? What is the preimage of a point? Okay, so let's do an example. So here's a map from the plane to the real number line. It assigns a point in the plane to this number. So for example, 2, 1 goes to 4 plus 1 equals 5. Okay, so the point 2, 1 gets mapped over by f to the point on the number line. This is 0, 1, 2, 3, 4. This is 0, 1, 2, 3, 4, 5. So f maps this thing here. Okay, this is R2. This is just a cartoon. This is the formula for our map. Okay, so what was the question again? What is the preimage of a point? Okay, so let's look at, well, why not 5? So what is the preimage? So the preimage of a point in the output space, output space, is the set of all inputs that map to that specific output. Okay, well, I answered the question. This is the definition of preimage of a point. The preimage of a point is that. So let's do the example. The preimage of the point 5, preimage of 5 is, in this case, it'll be a circle, is a circle of radius square root of 5. Okay, so you see that there are infinitely many points in the input space that all get mapped to the number 5. Okay, so for example, this point is 0, root 5, and let's plug it in. 0, root 5 gets mapped to the point, 0 squared plus root 5 squared. Well, that is 0 plus 5, which is 5. Okay? Other points like 0, 0 is not in the preimage of 5 because 0, 0 gets mapped to 0 squared plus 0 squared, which is 0. That is not 5. Next, what is the graph of a map? Okay, so let's do an example. This is a map from R to R, and let's call it F. And so the graph of a map takes place in a bigger space. R, the input space, times, like a set times, this is called Cartesian product, with the output space. We put them together. And actually this is just the plane R2. And so the graph actually lives in the plane. In this example, it looks like this. This is the graph. a point on the graph here is a tuple x comma f of x, if this is f. And all these points have that form, x comma f of x. So like this one looks like I took -1 comma f of -1, which is -1 comma 1 because we're squaring. That's what f of -1 is. This one, okay, let's choose a different one. Let's choose this one here. This would be maybe the point √2 comma f of √2, which is the point √2 comma √2 squared. F of √2 is √2 squared, which is 2. This one looks like this one here looks like it's 1 comma 1 squared, which is 1 comma 1. Another example. So t maps to two numbers, t squared and t to the third. Let's call that f. We seem to always call our maps by the name f, but we can call them other things. Okay, well, let's call it g. Or let's call it Alex. Okay. So if I take the graph of this, now I need to do like the whole input space cross the output space will create a bigger space. In this case, it's a 3-dimensional space. So the graph lives in 3 dimensions, and I chose this example because I know the answer. This little dotted line here is a parabola in the first 2 coordinate planes. Like if I give coordinates y1, y2, y3 to my 3-dimensional space, y1, y2, y3, then here's the graph. It sort of twists around and down, and we'll do this in this example more. But the graph here, a point on this graph is a point t comma, I called it Alex, the map Alex of t, which is, in this case, t comma t squared t to the third, because Alex of t has output values in R2, so we actually need 2 numbers for, this could have been f of t, but I was feeling like making a point, because often in computer you name your functions with like words that are descriptive of what they do. So a better name would have been like twist. So then I could have called it like twist of t. That's more descriptive of this map, of this function. Okay, so for example, like 1, 1, 1 is on the graph somewhere, but also 2, 4, 8 is on the graph, because 2 maps to 4, 8. And so it's on the graph. So what is the graph of a map? The set of points x, f of x inside the bigger space formed by inputs and outputs. That's it. If the graph of a map called f. Okay. What is a sample of points from a geometric object? So a sample of points, or a sample, is just a list. It's just a list of points. So here, these points are each in R2, is an element of R2. This is an element of R2. This is an element of R2. So I have a list of points in R2. So I can draw R2. I can start drawing these points. 1, 0 is that point. 0, 1 is that point. Square root 2 over 2, comma, square root 2 over 2 is that point. -1, 0 is that point. 0, -1 is that point. And so actually, if I kept doing this list, you can imagine I'm sampling points sampling points. This is an abbreviation for points from a circle. And so in experiments in science, you might have data that you're collecting, and that data is a sample of points in some geometric object. Like if you have a brain, this is supposed to be a brain. I don't know, squiggly. It's a brain. And let's say you attach electrodes to the brain at different locations. Then you collect, at each moment in time, you look at the electricity or the electric current amplitude, something, I don't know, I'm just making something up here, at each of these 5 points. Well then, at each time you measure, 5 numbers, because you had 5 electrodes, 1, 2, 3, 4, 5. That is a point in 5-dimensional space. And so you're sampling points, and those points probably are not just randomly sampled from R5. They might lie on a geometric object, like these points lie on a circle. Okay, what is a sample of points? A list of points from the object. Okay, what is a vector field? Okay, use the previous example. Let's see, what previous example? I actually meant this one up here. This was one of our first examples. So when a map goes from the input space and output space are the same, we can visualize them as separate spaces, like here's the input space, here are the outputs. Or we can visualize them a little differently, and this is called a vector field. So the point 1, 0 went to the point 0, 1, which is up here. But what I can do is attach to the point 1, 0 the vector that's pointing towards that point. Here's this purple point, and here was its output. The purple 1, 1 got assigned negative 1, 1. So at the point 1, 1, I can assign the vector negative 1, 1, and I'll draw it like that, attached to this point. And now this pink point here got assigned this point, so 0, 1 was this pink point over here, and it got assigned negative 1, 0, and I view this now as a vector, and I attach it to the pink point like that. So you can imagine that this map is a vector field. Vector field, those are just 2 words. What they mean is at every point you attach a vector. Sometimes those vectors are longer, sometimes they're shorter. But at every point you attach a vector, and that is a vector field. Every single point in the input space has hovering above it a vector. And so let's actually pause and go to my computer. Share screen, desktop. Okay, let's go here, and let's go to vector fields. So here you see a picture of many of the points of the vector field, sine y, comma sine x. This is really the map x, comma y maps to sine of y, comma sine of x. And maybe there's other, here's more vector fields. Here's a vector field on a sphere, so every point of a sphere we will attach a vector. The flow field around an airplane is a vector field. Let's look at that. Whoa. That's pretty cool. I did not actually look at this Wikipedia page in detail, but these are actually called integral curves. We'll learn about that later. Let's look at, there's this, field play. Okay, so here's a vector field, sort of visualized by, at each point, then moves in the direction of the vector. So let's do our example that we did in class, which was minus y, comma, x. So there we have that vector field we just did on paper. It's just swirling around in circles. And so actually a vector field, if you pick a point and then you follow the motion of that point, you will get a curve. So a vector field is one way to describe curves. It describes many curves, like it describes really big circles. It just depends on what point you start. And then that point will trace out a curve as it evolves, moving in the direction of the vector field at every moment. So let's click randomize so you can see interesting vector fields. So here's the vector field whose first component is x and whose second component is the sine of x over x, so sine of 1. Okay, that was weird. Let's randomize again. Here's a vector field visualized as the first component is the y is y, comma, x divided by, why is it x divided by x again? Probably because I changed it. Okay, so now it's something more interesting. Let's randomize now. Well, anyway, so you can see that there are many different vector fields and they have interesting behaviors. Very cool. Okay, let's go back to the... Okay, so now we're almost done. So what is a vector field? A map, assigns a vector to every point. So it's again a map. So a vector field is a map. It assigns a vector to every point. So for example, R2 to R2 would assign a vector every point. But also, like, you could assign a vector to every point in R3. Every point in R3 gets a vector in R3. Yeah, and there's more complicated things, like you could say, let's take a sphere. Let's take a sphere and assign to it vectors in R3, so at every point gets a vector. That's sort of interesting. And so this is a vector field. It's a map. It assigns a vector to every point in the input space. What's a system of inequalities? What is a system of inequalities? Okay, so here's our example. So here is a geometric object. It's shaded in. And let's describe it. So if I give coordinates x1, x2 to this is my little R2, so I've just named the coordinates, given them names, then I could say that this set here is described by what inequalities? Well, x2 equals x1 squared would be this curve. But I don't want that curve. What I want is everything below the curve. So actually this will be less than or equal to x2. Yeah. So inequalities are hardest. Inequalities are the hardest thing. Most difficult. Yeah. So that's not it. That would just give me, why this parabola continues forever. That would get, if I just wrote down one equality, it would be like everything below the parabola. It wouldn't have this stuff over here, but it'd have all those other things. So we need more. We need more inequalities. Let's say that x1 is less than or equal to 1. That's like saying everything over here. And then let's say that x2 is greater than 0. So all three of the inequalities together give that little piece. It should be curvy. There we go. Okay, so a system of inequalities is a list of inequality expressions or symbols or formulas. That's what it is. Okay, great. So we covered all the topics and concepts for problems 1 through 3.